So, in today's session, we are in the framework of photonics, which is the field of controlling and manipulating the properties of light down to the nanoscale. In particular, in the framework of the FNIP program, we want to explore how photonics is advancing the design and fabrication of optical components and systems for applications to advanced microscopy and imaging. In particular, today, we move to the single photon regime, investigating one of the four pillars of the so-called second quantum revolution that we are experiencing in these years. We are in the field, in particular, of quantum imaging and metrology. The first speaker will be Dr. Giuseppe Ortolano from the Italian National Institute for Metrology in Torino, Italy, presenting the application in quantum hypothesis testing, quantum reading, and pattern recognition. The second speaker of the day will be Professor Daniele Faccio from the University of Glasgow in the UK, talking about ongoing Mandel microscopy and fluorescence lifetime imaging. And the first speaker will be Dr. Oleg Varnavsky from the University of Michigan in the US, presenting the latest results in scanning fluorescence microscope with entangled two-photon excitation. I'd like to thank all the speakers again for being here today, and thanks again to all the participants. Now I leave the stage to Professor Gianmichele Ratto, who will introduce the first speaker of the day. Thank you.
The first speaker is Giuseppe Ortolano. He's a researcher at the quantum optic groups at the INRIM Institute. It's the Italian institute that basically makes sure that metrology is done properly in this country. Not a simple task in Italy, to be honest. He is working on quantum techniques to improve classical schemes. He got his master's degree in physics of complex systems from the University of Turin in 2019. He did his PhD in physics at Politecnico di Torino, and his interest is mainly on quantum information and quantum optics. He has treated different problems in quantum metrology and quantum hypothesis testing, both theoretically and experimentally. The title of the talk will be Application in Quantum Hypothesis Testing, Quantum Reading and Pattern Recognition. Thank you very much, Giuseppe, for being with us, and the stage is yours.
Thank you. Thank you very much for the introduction. I will share the screen now. All right. Can you see my screen? Yes?
Well.
Okay. So, yeah, I'm Giuseppe Ortolano, and today we'll talk about the work, some of the work carried on at the Quantum Optics Group at the Metrological Institute of the Italian Metrological Institute in Turin. And in particular, I will talk about applications in quantum metrology and hypothesis testing in the optical domain. These are subfield of quantum sensing, in which in general the objective is to beat classical limits using quantum resources. This is done, for example, in quantum metrology in tasks such as interferometry, in which you want to estimate a size parameter, and they use quantum resources to exceed the accuracy that that you can achieve classically. Or, for example, in absorption imaging, or in the characterization of instruments for other quantum technologies, such as communication, quantum key distribution, and the likes. And in the setting of hypothesis testing is done, for example, and I will talk about this more in detail later, for the readout of digital classical memory, such as DVDs. Or for target detection, that may be the case, for example, in the LiDAR that are used in the self-driving cars, in which one uses the status of light to see if there are obstacles in the way. So, what are the classical limits? Well, in estimation, there is a fundamental limit for classical state, that's the shot noise limit. In the context of optical state, the short noise limit tells you that when you use a state to estimate a parameter, a physical parameter, with having n photons, the uncertainty of your estimation, that can be, for example, a phase estimation, displacement estimation, or an estimation of a loss absorption parameter, scales as the inverse of the square root of the number of photons that you're using. So in general, if you want to increase the accuracy of your estimation, you want to reduce the uncertainty, what you can do is to increase the energy used in the estimation. Well, this is not always the case that you can do that. For example, when you consider large-scale interferometers used for gravitational wave detection, the energy is already so high that increasing it even more would bring a level of technical noise that would offset the advantage in using more energy. Or, for example, when you're probing biological samples, there might be some photosensitivity. That means that there is some energy threshold after which you can damage the sample. So you have an hard limit on the amount of energy that you can use. And if you want to estimate the absorption of faint object, quantum resources can be very useful. And finally, sometimes you just want to investigate a phenomenon that intrinsically are at the single photon or few photon levels, that you cannot do this with, and you cannot do this with the classical state. And these phenomena are, for example, phototransduction that in the retina, or photosynthesis, or as I already mentioned, the characterization of instruments for quantum technology, such as a single photon detector. So how do you beat these classical limits? Well, the short noise limit is based on the fact that photons in classical sources are independent from each other, basically. So, in fact, the scaling given by the short noise is the same scaling that one has when repeats independent measurements n times. So, using quantum resources enables to beat this limit because of quantum correlation. That is a degree of cooperation in the quantum states that's not available in classical ones. And this extra information can be used to enhance the results. Well, classical correlation, quantum correlations can be manifest in different ways. Maybe arguably the most famous one is entanglement. That is this global property that cannot be described in terms of single subsistence. Another one that is related to the quantum nature of the electromagnetic field is squeezing. That is, for example, what is used to enhance the interferometers. And finally, one can use the properties on the photon number distribution of the state analyzed, the state used. And this is what I was focused on. One instance is single photon sources, that is 4 sources that emit deterministically a single or few photons. And the other one, it's a non-classical correlation in the photon number, in which you have basically a source that's composed of 2 beams of light that may be classical by each other, but their fluctuation are perfectly correlated. And this is a quantum feature. So this non-classically correlated sources, how they are produced? Well, one way to produce them is the phenomenon of spontaneous parametric downconversion. In this phenomenon, basically what happens is that you use a laser and you make it interact with a nonlinear crystal. And what happens inside the crystal is that with low probability, some photons of the laser are down-converted into a couple of photons that, of course, have to conserve energy and momentum. So this conservation of momentum means that the photons produced are anti-correlated in momentum. And this anti-correlation in momentum can be translated in spatial correlations by optical lenses, if needed. And what you have basically at the output are 2 beams that are not ordered by each other, but their fluctuation, their disorder is perfectly correlated. And you can use this correlation to actually improve some schemes. Intuitively, what you do basically is you use one of the beams, for example, to interact with an object that you want to analyze, and the other beams you can measure to reduce the statistical fluctuation. A way to quantize the degree of correlation is the so-called noise reaction factor. That's basically the variance of the difference between the photon counts in one beam and the other over their mean value. And this is an important metric because it can be shown that for classical light, the noise reaction factor is always bigger than 1. So measuring actually a noise reaction factor less than 1 is a signature of no classical correlation. Ideally, the process described will give perfectly correlated beams, but in practice, what you have is that you have experimental inefficiencies in detecting correlated photons that results in a reduction of this correlation that you measure practically. And it's expressed by this coefficient eta, that's the efficiency that you have in your setup. So I will show now some application, in particular to the estimation of a loss parameter. It was when you want to estimate the absorption of an object, what you do is basically you just use one state, you make it interact with your object, and then you measure your state after the interaction, and this way you can estimate your parameter, your loss parameter. For example, you have n photons after the interaction, the number of photons measured will be reduced. Well, as I already mentioned, the classical sources are limited by the shot noise limit, that is reported here in red. And it was shown that various quantum sources, among which the correlated one that I discussed, are bounded by another limit. That's the ultimate quantum limit. And you can see that this ultimate quantum limit offers an advantage, especially in the region of low alpha, that's dramatic over the classical shot noise. Here I show some experimental results that have been obtained in my group. Here in red, there is the shot noise limit, that the classical limit, while in dashed line is the theoretical ultimate quantum limit obtained with ideal sources. Well, in yellow, there is the results that can be obtained with state-of-the-art experimental setups that, of course, are worse than the ultimate quantum limit because of this efficiency that I mentioned that's not perfect in an experimental demonstration, but still offers a dramatic gain advantage over the classical performance in certain regimes. Another thing I wanted to point out is that if you try and do something similar, that is use correlation with classical sources, for example, you can obtain classical correlation by using thermal state and splitting them with a beam splitter. You cannot reach an advantage. In fact, here on the upper side is reported the results obtained with classical correlation. In fact, you don't even reach the best possible classical estimation with this. So the advantage lays in the quantum nature of the correlation. On the same note, one can perform estimating the absorption imaging. That is, instead of having just one parameter alpha, you have a matrix of pixels, each having some kind of absorption. And using the same source, you can illuminate your object, and one beam will give you your absorption image on one side, And then the other one will give you the noise fluctuation of your beam, the starting noise fluctuation. So for example, one way to enhance your imaging is just to do the difference. Then there are more sophisticated post-processing. However, the result is that you have an improvement in your final imaging. This is our experimental results, also obtained in my group, in which here I show one instance of quantum enhancement that can obtain in a complete image, in which here you have a phi, and it's clear that quantum resources give you a much better visibility. So finally, before going to the part of hypothesis testing, I want to mention another application in metrology that we are working on. We just finished working on this. That is an application on the non-interferometric phase retrieval. I already mentioned interferometry, but when you have a phase object, another way to recover information is to use the effect of the phase on the propagation of light. There are classically a lot of non-interferometry schemes, but up until now there is not a lot of research on how this non-interferometric scheme can be enhanced by quantum correlations and quantum resources, and so we worked on that, and we showed that in a scheme like that's able to reconstruct the phase of an object with the spatial resolution and in a quantitative way, that are important things from an applicative standpoint. Quantum resources give an advantage. These are also experimental results in which you see that a grid of points can be reconstructed in a much clearer way using quantum correlations rather than the classical way. Now I will go onto the second part of my talk that's dedicated to quantum hypothesis testing, in which instead of estimating an unknown parameter, you want to discriminate two possible values of this parameter. So for example, for a loss or a transmission, you have two possible values and want to say if it is one or the other. Well, this finds application, for example, in the readout of optical memories, that then can be carried on into the detection of more global features such as pattern recognition in certain samples. And I will talk about these two possible applications. But first, let me introduce the problem of quantum hypothesis testing in a more formal way. Basically, in quantum hypothesis testing, you try to discriminate between two hypotheses, H0 and H1, by performing a measurement on a quantum state. The most simple example that you can give about on quantum hypothesis testing is the binary state discrimination, in which you have a state, rho, and you have to decide if it is rho 0 or rho 1. And this problem has been resolved many years ago with both giving the objective is to find the minimum probability of error in the discrimination, and the measurement that you have to perform to obtain this minimum probability of error. A slightly more complicated hypothesis testing problem is quantum channel discrimination. In a quantum channel discrimination problem, you want to discriminate between two quantum channels. What are quantum channels? Quantum channels are basically describe evolution of a quantum state, and in practical terms describe the evolution of a quantum state after, for example, the interaction with an object. So let's say that you have a quantum state, you probe an object. After the interaction with an object, your state will evolve according to this quantum channel. And then you have to discriminate if the object was described by the quantum channel E0 or E1. And in the application that I will show, the quantum channel in particular will be quantum loss channel. And so basically the task is to discriminate between two possible values of transmission, tau 0 or tau 1. This, as I mentioned, find application in the model in the readout of digital memories. And this problem was first proposed and analyzed in the protocol of quantum reading, in which it was shown that in the readout of a single cell of a digital memory, there is an advantage in using quantum resources. How is this done? Well, when you read out, when you read a single pixel of a digital memory, basically what you do is you illuminate it with a given optical state, and then you measure the output after the interaction to decide whether the bit is 0, that is encoded into 0, or 1, this is that is the reflectivity or transmissivity of your cell is tau 1. So in this setting, a limit can be found on the performance achieved by classical states, and it can be shown that with an optimal measurement, that it's a theoretical measurement. I mean, you can write the measurement, but it's really not easy to perform it. And this point I will return on it later. You can find a theoretical limit on the performance of classical states, and then you simply show that there are quantum states. For example, the correlated states that I showed before, that are able to beat this limit, again with an optimal specified measurement in this case. And this shows a theoretical advantage in this task. Well, what we did recently was a practical implementation and the first experimental demonstration of advantage in this task by proposing a practical receiver that's just a receiver based on photon counting on the signal that is the beam interacting with the object and a correlated reference beam. And after that, just doing optimal post-processing on the output photon counts. And we showed that this relatively simple receiver is actually close to the theoretical optimal performance analyzed in the original proposal. And here I will show some comparison between the quantum performance in the classical one. In this graphics, what is plotted is the advantage in terms of bit recovered by the procedure. So on the left, we show the ideal situation in which you have perfect efficiency, and you can see that the advantage in certain regions reaches almost 1. One bit of advantage means that the quantum strategy is able to recover the bit with perfect reliability, while the classical strategy basically guesses, doesn't recover any information from the measurement. So it is of course a dramatic improvement. But on the other hand, as I already mentioned, for metrological application, when you perform an experiment, you have to take into account that you will have an inefficiency. So on the right, I reported the performance that you obtain with less than ideal efficiency setup. And we report an advantage of, we predicted an advantage of 0.15 bits. That this is still a good advantage because it's advantage per cell. So if you consider that a classical memory usually has a very, very large number of bits, the practical advantage can be dramatic. So we performed the experiment. And here I report the experimental data. In blue, it's the fit of what I showed in the previous slide, our experimental point referring to this situation. Well, in red, there is the advantage. I mentioned before that the optimal classical receiver was achieved with a a theoretical measurement that it is not clear how to actually perform. So this is the advantage of our theoretical bound. While in red, they report the advantage of a classical strategy paired with the same receiver of the quantum one that is just performing photon counting and optimal cross-processing. And on the upper end, I report what I think it's a nice visualization of what quantum resources bring and how the origin of the improvement. And so this is the joint photon number distribution. In blue, there is one hypothesis. In red, there is the other one. And there is very good distinguishability. While on the right, you have the marginal distribution that is what is accessible by classical resources, in which, of course, the distinguishability is much less. And this is the origin of the quantum advantage, basically. So here I will skip because I don't have much time. Finally, I will talk about how this advantage in the sensing readout of local properties such as a single bit of an optical memory translate to more complex domains such as the detection of global features, that is the objective of pattern recognition, for example. So the question is just, since in pattern recognition and detecting global features, a lot of classical complex processing are available, is the quantum sensing advantage lost or is still preserved in this more complex task? Well, to investigate this problem, we analyze the problem of handwritten digit recognition. That is a very common test bed for this kind of pattern recognition problems. So what we did is that you have your ideal digits. After the sensing procedure, you have you reconstruct your image with some bit flip that are given by the strategies you're using to perform sensing. And you are interested in the classification error that is related by a highly nonlinear map that depends on the classification that you are using to your bit flip sensing error. We perform the classification with two different post-processing. One is almost one of the most simple that you can use, that is the nearest neighbor, that basically classify an image using a database. You find the closest image to the unknown one in your database, and you assign the class of your closest image in the database to your image. And the other one is a more sophisticated machine learning technique. It's a convolutional neural network that's basically the state of the art for pattern recognition. It's the one that's able to achieve convolutional neural network architectures are the one that are able to achieve the minimum error probability in absolute in the handwritten recognition task. So we performed the experiment on this. We analyzed the image classically and and quantum mechanically with quantum sources, with classical and quantum sources. We classified them, and these are the results, the experimental results. On the left, I report the single error probability as a function of the encoding transmission of the bit 0 and 1 of the binary images. And in blue, there is the quantum performance. In green, there is the theoretical best classical one that it's again obtained, as it was the case in quantum reading, with a highly theoretical measurement that is not clear that can be actually practically performed. When in red, there is the classical performance with photon counting, same as in the quantum case. And on the right, I report the classification error. So you can see that, of course, there is a nonlinear map, as I anticipated, between the single pixel bit flip probability and the classification error in the pattern recognition task. And we show, if we're looking at the graphic, we can see that not only the advantage is preserved, but there are certain regions in which there's a significant amplification of this advantage, showing that, yeah, the sensing, in fact, it is useful also when considering the detection of global properties. And just to show that it does not depend on the classification error, on the classification algorithm chosen, that in the previous slide was K nearest neighbor. Here I report also the classification error with the convolutional neural network, and the qualitative behavior is very similar. And it shows that no matter how sophisticated the post-processing is, the quantum sensing advantage is preserved, and it's useful also in the detection of global property that we think is an important question to answer in view of application of these quantum enhanced measurements. So just to conclude, I gave you an overview of how quantum resources can be used to improve the metrological task of estimating a loss parameter. Then I showed how an experimental quantum advantage can be obtained in the readout of a digital memory. And after that, I showed how this quantum sensing this quantum sensing advantage scales also to the detection of global properties and more complex domains such as pattern recognition. And I thank you for your attention.